Hello and welcome to this practical training session for the Copernicus Marine Service Workshop, MarineData4Africa. My name is Ergane and I'm going to be your trainer for this session. So this Python training session for this workshop consists of 4 notebooks, 1 introduction and then 3 exercises. And this is the video. This video is about the 4th notebook, so the last exercise about cyclones and especially about monitoring the Eloise cyclone's effect on the ocean parameters. So these are Jupyter Notebooks. They consist of both text and code cells. And if you want to run one cell, you can click on the arrow on the top menu, or you can also use the keyboard shortcuts Shift and Enter. So tropical cyclones can be very dangerous as they bring very violent winds, heavy rains and high waves. In some cases they also bring floods, and therefore they have dramatic consequences on humans and infrastructure. The Eloise cyclone occurred in the Southwest Indian Ocean from January 14th to January 25th, 2021. It has killed over 27 people, and the damage from the storm is estimated to over $10 million US. So this is a picture, a satellite photo of the Eloise cyclone. And so such cyclone, it's crucial to be able to monitor them. And this is what this exercise will focus on. Thanks to the Copernicus Marine Service product, we are able to study the effects of such cyclones. So the data that we're going to use to follow the cyclone and to monitor its effects are the winds, the temperature, the waves, and the location of the cyclone, its path. We are going to study the cyclone from January 10th to January 27th. And this is the geographical region that we are going to study. So we are studying the cyclone from different, with different parameters from different products. Regarding the wind, we will study it from wind observation, global wind observation product. So if you click on the link here, you will access the web page of the product from the Copernicus Marine Service catalog. And you can also check on the documents about the information about the product and about its quality. Here you have the link to the 2 documents. We're going to study the temperature from both model and observation products. So for the first one, it will be from the Global Analysis Forecast Physics model. Here, again, you can click on the link and check on the documents. And for the observations, we will study it from this sea surface temperature observation. Again, you can check on the web pages to have more information about this product. The last Copernicus Marine Service product we're going to use is the wave model. So Global Analysis Forecast Wave Model. And as for the others, you have its web page and its documents here. So all the products mentioned before, they are available in the Copernicus Marine Service catalog. But the last one, the location of the cyclone, that gives the coordinates of the cyclone at for each date every 3 hours. We have downloaded it from the NOAA website, so it's called IPTRAC's website. You can explore the website here. There's the link. And so this is what we're going to use to see where the cyclone is located. All the data that I presented, they have already been downloaded for this training. And they are all available here in the data directory here. If you want to download some data by yourself, if you want to study another cyclone, therefore on another region and over another period, you may need to download some data by yourself. And you can check on the introduction notebook, which explains the different ways to download such products. These introduction notebooks will also show you how to handle NetCDF files within Python. And so if you're new to this concept, you may need to read this introduction notebook first. So we can now begin our exercise, and we can start to monitor the Eloise cyclone effects on the ocean. The first step before running a notebook, before running some Python code, is to import the libraries. So we are going to use 4 libraries here: NumPy, Xarray, Matplotlib, and Cartopy. You can click on the links here to have a more detailed, to have information about how you can use these libraries. And so we need to import the libraries first. So we run this cell. Then we load the product's data. So as I said, as we've seen, the data are stored in the data directory, and so we tell Python where the data are located, and then we open the NetCDF files with the command open dataset. We have therefore 5 variables: the observation SST, the model SST, the model wave, the observation wind, and the track. Track refers to the location of the cyclone. To check on the product's dimensions and variables, variable names, you can run, you just have to put the name of your variable in a cell and run it, and then you'll see its dimension, coordinates, and variables. The first plot we're going to do for this exercise will be the wind evolution. And we're going to see how the wind maps match the location of the cyclone. So we are going to start by, so we're going to plot, so we are going to plot a map for each date. And so we select the date from the track. So this first line takes the date from the track. Then we define the characteristics of the figure we want for this one date. So we define its size, we define its projection, we add the coastlines, we put the longitude and latitude lines and remove the labels on the right and on the top. We add the land mask, we set the extent of the map, we add the title, and finally we adjust the space around the map. This line, with this line, we take the closest data to the date from the wind observation, so as to plot the wind for the right date. So we use the cell command from Xarray, and we choose we select the nearest data. Then we will map the wind speed. So we use the pcolor function. We define the longitude, latitude, and then wind speed. You can change the minimum and maximum values of the color map. You can also change the color map, like if you want reds or blues. So I've chosen blues here. And then we will add the location of the cyclone, and therefore we'll use a scatter plot. Finally, we add the legend of the figure, and then we save it. So if we run this command line, it might take some time, but in the end, you will see the figures below. So you can see here that the figures have appeared, and they have also been saved in the out directory. So they are the wind figures. Oops. So if you click on it, you should be able to open the figures. An easiest way to see the information will be to display an animation. And to do so, we import the modules first. So we just run the following cells. Then we search for all the files that start with wind, as this is how we have named our figures before. So we run this cell, then we save the GIF, and then we display it. So we can see on this figure, on this animation, that in black, this is the location of the cyclone, and in the background, it's the wind speed. We can see that indeed the cyclone has generated heavy winds, and that the winds match perfectly the location of the cyclone. We're going to see now, we're going to do the same kind of animation, but with waves, and see how the cyclone has affected the waves. So you can check before if you want how the wave model is structured, especially to access the names of the variables. And again, we do the same thing. So we have a loop on the dates. We select the date from the track. We define the characteristics of the figure. Sorry. We select the nearest time step to retrieve the date from the wave model. We plot the wave height on the background, and we also add the location of the cyclone on top of it. We add the legend, we save the figure. So you can run this cell. I have added the line close here, so as the figures will not appear as they did before, like here, for example. The figure will not appear, but they will be saved in the same folder out, and we are going to make an animation from it. So we run this cell, and we can see the evolution of the cyclone, and as well as the evolution of the wave height. The colors of the dots here refer to the wind intensity, whereas the red colors refer to the wave height. We can see again, just like we did for the wind, that the wave height matches perfectly with the location of the cyclone, and the strongest winds generated the highest waves. The last figure that we're going to plot, the last animation, will be we're going to study the sea surface temperature, so from a model product and from an observation product. Again, we use almost the same code, except that the temperature products have a lowest resolution. Therefore, we take one time step in 8, and so we do the same. Well, we plot the same kind of information. And then we can plot the animation. So on the left here is the model SST, and on the right is the observation SST. So we can see that the time resolution is not as good as for the winds of the waves, or the waves, for example. Again, the blue dots refer to the wind speed, whereas the backgrounds refer to the sea surface temperature. It's not, the results of this animation are not as obvious as for the previous ones. Still, we can see that when the cyclone reaches the west of the Madagascar island, the temperature strongly decreases compared to before the cyclone arrived. And so this is one of the conclusions we can make, that the temperature, the sea surface temperature decreases from, well, with the cyclone. So this exercise has shown you how you can use the Copernicus Marine Service products to follow and monitor the cyclone and its consequences. We have studied its consequences on winds, wave height, and sea surface temperature. And so you're now able to follow any cyclone anywhere. And now this is the end of our last Jupyter Notebook video. Thank you for watching. I hope you enjoy it. And if you haven't seen the other exercises, you might be interested in it. Bye.